Next item is a theorem, which basically the differentiation rules theorem. Most of this stuff is trivial except for few at the end. So, differentiation rule theorem. So if we start with a supposition, we have two vectors that are differential. So u and v are differential vectors. We have a scalar c, as you can expect, scalar multiplication, and we have a function f that is a real valued function. Remember, we talked about vector valued functions, what we are dealing with now, and when we had the single variable calculus, those functions were real valued function. Now we are talking about vector valued function. So having all these suppositions, then we have the following 6 rules or properties. If we take the sum or difference of two vectors, then we'll have the sum or difference of their derivatives. Sum or difference. Let me change the notation just here. Shortcut. Write it simply as u prime plus or minus v prime. It's obvious property or rule. What happens if we take the derivative of a constant that multiply a vector? Well, the same as with a single variable or real valued, it will be c, the constant, times the derivative of the vector. How about when you have a function, not a scalar c, but a function f of t that multiply a vector u of t? So you have a product of two factors. The first factor is a function, real value function, and the second is a vector. But both are function of t. So what did we do in Calc 1? What rule we used to deal with a product of two functions? The product rule, right? So it will be the same thing, but the product rule will apply here. So we'll have f prime of t times u of t plus f of t. Remember, this is still a function, and times u prime, the vector u prime of t. All right, so this was nice. What happens if we have a vector? I'm sorry, there was a question or comment? What happens if you have two vectors with a dot product in between? Like so. Okay? Well, the product rule still will be applicable here. But now, remember, this is a dot product, so the result is a scalar. So we're going to have u prime of t times v prime plus u dot, I'm sorry, I said per time, but all of those are, all the multiplication here is a dot product multiplication because we are dealing with two vectors. So u prime dot v plus u dot v prime. What if we have cross product turn out that the product is a product, and the derivative of a cross product will result with the same product rule, except the product will going to remain a cross product. So it will be u prime cross of v plus u cross v prime. Lastly, the last property, what common rule we didn't use yet? Well, how do you do quotient of two vectors? But what else we did use? Very common rule, chain rule. If you have a composition, and a vector u, instead of a function of t, is a function of f of t, like so. So, in real valued calculus, we had u df, df dt. Remember that this is cumulative, so we could have written it as df dt, or f prime times u prime, and that's exactly what we'll have here. It will be f prime of t times u prime of f. Those are the 6 rules. All right? And I think we have time for one example.
Is that u prime of the ft or u prime?
Yeah, u prime of f. I tell you what, let's do integrals. The theorem applies for integrals, the same thing. Again, if r, so I'm not going to do an example here, I'll just do an integral. If r is a vector f of t, g of t, h of t, like so, and they're all integrable, then we have the following property, the integral, and I'll do the definite integral, so from t equals a to t equals b of r of t dt going to be the integral, the vector where each component is an integral. So it will be the integral of from a to b of f of t dt. That will be in the one position, and then the integral from a to b of g of t dt, and then the integral from a to b of h of t dt. What do we do if we don't have a definite integral? Then we have that constant, remember? So for instance, this example, we integrate the following vector, 2 cosine t sine t and 2t, like so. The solution, this is another helix. The solution, the integral, this is indefinite integral. So it will be a vector that has this component, the integral of 2 cosine t dt, integral of sine t dt, and the integral of 2t dt, close the vector, and it will be the integral of 2 cosine is 2 sine t, And then here we have the integral of the sine is the cosine. It's a cosine still. And the integral of 2t is t squared over 2, 2 times t squared over 2, or t squared. What about the c? Plus a vector or a constant c. And that's what the point of this exercise, where c is a constant, is a constant vector, or a vector constant. Okay, guys, the integral of the sine is the cosine.
The derivative of
Did I say it's a negative? You're right. You're right. All right. You caught me here. Is the vector constant of the integration. All right. I missed one example, which is a nice example, but you rushed me, so you want to get out. Shall I give you one more example? A quick one? It's a quick one. It's a 1 minute example. You asked already. Go ahead.
The cross product results in a vector with the derivative of the cross product. Would you be able to work out the cross product first?
Yeah, the cross product, the derivative of cross product is, of course, a vector.
No, I was asking since the cross product is a vector, would we be able to work out the cross product and find the derivative of that vector? Would that be the same as what the rule we just found out was?
You have to do the two because you have two cross products. But yes, the answer is yes.